Now we start our lectures on the kinetics of biological reactions. We have talked about the energetics and stoichiometry of the biological reactions and found their relationship with the team model. This gives us ideas about the direction and ratio of the mass and energy flow. But to describe the biological processes comprehensively, we still need to understand the rate of reaction, which brings us to the kinetics. Biological reactions, in essence, are enzymatic reactions. Enzymes can reduce the activation energy for a biochemical reaction, making it thermodynamically easier to occur. To understand the kinetics of enzymatic reactions, let's look at the simple model of the enzymatic reaction. The substrate first binds to an enzyme to form an enzyme-substrate complex. Then the substrate is degraded to products and released from the free enzyme. Let's use E to represent the enzyme, S to represent the substrate, and P to represent the product. ES is the enzyme-substrate complex. K represents the reaction rate with a unit of per hour. Two empirical reactions can be used to describe the enzymatic reaction model: the formation of enzyme-substrate complex and the breakdown and release of the product. K1 represents the complex formation rate, and the K-1 represents the dissociation rate of the complex back to free enzyme and substrate without degradation. K2 is a product release rate, while K-2 is a rebinding rate of the product onto the free enzyme, which should be negligible. Square bracket E is the total enzyme concentration that includes the free enzyme and complexed enzyme. Square bracket ES is the concentration of the complexed enzyme. Therefore, the concentration of free enzyme is square bracket E minus square bracket ES. So, the production rate of the complex enzyme, DES dt, is the result of Ki times the free enzyme concentration times the substrate concentration, plus K-2 times the free enzyme concentration times the product concentration. The second half of this equation, however, is negligible. The breakdown rate of the complex enzyme, on the other hand, is the result of K-1 times the complex enzyme concentration plus K2 times the complex enzyme concentration. At steady state, the production rate should equal to the breakdown rate. After rearranging the equation, we can group the reaction rates to a constant K sub S, and then write the expression for the complex enzyme ES. Because what we really want to know is the generation rate of the product, mu, which can be expressed as mu equals to ES times K2. We can substitute the ES with the previous equation. When there is abundant substrate, all enzymes are complexed. So the max product generation rate, mu max, equals to K2 times E. Substituting this to get the monokinetic equation. This is a very important equation that can be used to describe the growth rate of biomass and can be transformed to describe the consumption rate of substrates. It is used throughout this book and also extensively used in the field of chemical engineering, biological engineering, and environmental engineering. Now, let's analyze this equation. We can plot out this equation with the substrate concentration as the x-axis and the reaction rate mu as the y-axis. When the substrate concentration equals K sub S, the growth rate mu equals to half of the maximum growth rate. So K sub S is also known as the half saturation coefficient. when the substrate concentration S is far lower than K sub S, S plus K sub S in the denominator roughly equals to K sub S. So mu can be written as mu equals to mu max times S divided by K sub S. Because both mu max and K sub S are constants, mu is in a first order relationship with S. When S is far larger than K sub S, S plus K sub S roughly equals to S. Then mu equals to mu max, a zero order relationship. If there are two limiting substrates, the growth rate mu is determined by both substrates simultaneously. High concentrations of both substrate 1 and substrate 2 are needed for a fast growth rate. A decrease of either of the substrate concentrations can reduce the growth rate. An example of the multiple limiting substrates is the heterotroph that uses ammonia as nitrogen source. Both organic carbon and ammonia concentrations control its growth rate. Biological reactions or enzymatic reactions can be inhibited by various compounds, such as heavy metal, or even high concentrations of free ammonia, free acetic acid, and so on. To model the effect of inhibition on kinetics, we can summarize them into competitive and non-competitive inhibitions. In the competitive inhibition model, the inhibitor competes with the substrate for the active binding site on the enzyme, decreasing the chance that substrate can bind to the binding site. But if the substrate concentration is far higher than the inhibitor concentration, the effect of inhibitor on substrate binding is negligible, and the binding sites are constantly bound to substrates. Therefore, the maximum growth rate is not affected by the inhibitor. We can use this competitive inhibition function to modify the Monod equation. The inhibition function increases the K sub S in the denominator, therefore decreasing the growth rate. But when the S sub S is high enough, the growth rate should still equals to the maximum growth rate. When the inhibitor concentration is high, the inhibition function is high, increasing this K sub S term. So a higher substrate concentration is needed to reach maximum growth rate. We can plot this out. With the presence of the inhibitor, a higher S is needed to reach half saturation and maximum growth rate compared to the uninhibited reaction. Can you pause this video and try to plot out the curve for an inhibitor with a larger Ki value? An inhibitor with a large Ki value brings the inhibition function closer to 1, therefore has a diminished inhibitory effect compared to that with a small Ki value. As for non-competitive inhibition, the inhibitor binds on a different site from the substrate binding site, which renders the enzyme inactive and cannot degrade the substrate bound to it. This effectively decreases the enzyme concentration, hence the overall growth rate. Moreover, no matter how high the substrate concentration is, the maximum growth rate is lowered by the inhibitor due to the decreased enzyme concentration. Free ammonia inhibition to various biological processes is a non-competitive inhibition. The non-competitive inhibition can be described by this function that reduces the overall growth rate. When the inhibitor concentration Si increases, the inhibition function decreases, reducing the growth rate. This red line in the plot shows the inhibited reaction. The maximum growth rate becomes mu times Ki divided by Si plus Ki. And the half coefficient K sub S stay unchanged. Can you again think about the role of Ki in this function? Similar to competitive inhibition, a large Ki would mean a more diminished inhibitory effect. Besides the competitive and non-competitive inhibition models, sometimes the substrate itself becomes inhibitory at high concentrations. For example, free acetic acid can inhibit methanogens at high concentrations. Andrew's equation is used to describe the substrate inhibition. The denominator of the Monod equation is modified by an inhibition term S sub S squared divided by Ki. A high substrate concentration eventually brings down the growth rate. If the substrate has a large Ki value, its inhibitory effect is not as pronounced as those with a small Ki. Nonetheless, an infinitely large substrate concentration can bring the growth rate close to zero.